नो सर, बस उसमें थोड़ा बहुत ये जानते हैं सर कि जो लो फ्रीक्वेंसी में मेरा जो बॉडी प्लॉट में बनता है सर, उसी को एसिम्प्टोटिक बोलते हैं, जिस डायरेक्शन को फॉलो करता है आई थिंक।
I'm not talking about asymptotic asymptotic magnitude plot of Bode plot. I'm talking about the asymptotic phase plot. Do you know what asymptotic phase plot is?
नो नो।
Sir, in that plot, we just plot the angle of the magnitude plot that we have plotted.
No, no, that is a phase plot. Do you know how to draw an asymptotic phase plot? Are you aware of how to do that asymptotic phase plot? Now, Kirti, can you tell me what is the slope which is contributed by a single pole in asymptotic Bode phase plot?
So, poles give minus slope or plus. I'm just always confused between them.
Minus
Uh, Slope in negative direction, minus slope, like minus 20.
minus 20 dB per decade is the is the slope that you get in magnitude plot, not in phase plot. In phase plot there will be some degree, right? We are talking about magnitude over here. dB is magnitude. I'm talking about phase plot.
Yes, sir.
So phase plot is not known to anyone. Asymptotic phase plot.
नो।
Sir, 90 degrees.
90 degrees is the maximum phase that can be contributed by a pole. It is a maximum phase. I'm not talking about, you are not talking about the slope and for how much, for how much frequency it would exist. So Pooja, do you know asymptotic Bode phase plot? Rajnish, you can please unmute your mic or type in the window. You can just say whether yes or no, whether you know it or no, or you don't know it. Shadat,
नो सर।
did you say yes or no?
नो नो।
Okay. Ashutosh, do you know what asymptotic Bode phase plot is?
No, sir.
Sonali Kumari, sorry. Do you know what asymptotic Bode phase plot is?
सर, isn't the normal body phase plot?
No, it is not a normal Bode phase plot. You are from EC, right, Shadat?
Yes.
Okay, so there are several times where questions have come from asymptotic Bode phase plot. So what I can do is maybe so I have an exam coming on 20th October. So before that, I do not think I will find time for me. I have prepared a note for you people for this asymptotic Bode phase plot. You won't find this in most of the books. If you go, if you follow BC Kuo or if you follow Ogata, you will not get this thing in those books. There are very few books who have covered this asymptotic phase plot. Maybe you would get that in normal needs. But what I will do is maybe I have already prepared the notes, but we will discuss it maybe not today, maybe 2 days later, or I mean 2 weeks later or something. I have already prepared for it. You can just go through the notes that I have I'm going to explain, and that would be enough. You don't need to know anything more than what I will be teaching you in the notes. That will be enough for solving gate questions or any other. That the knowledge is uh, you know is enough for what if phase plot. So I will do
And
that maybe.
approximation to the body plot
Yes, yes.
is the asymptotic phase plot an approximation of the original body phase plot?
Yes, yes, right. Just like in just like in asymptotic Bode magnitude plot, you draw asymptotes to the actual plot. So 20 dB per decade that you say. So each pole will be after each pole will have a 20 dB per decade slope falling down. If there are two poles, 40 dB minus a 40 dB per decade. So similarly, you will also see that in asymptotic Bode phase plot. I will be teaching you that asymptotic Bode phase plot maybe a few days later or few weeks later rather. Okay, so let us start with today, and then if I find time, then let's see what we can discuss if we find. Let me present screen first. Is my screen visible?
Yes, yes.
Okay. Okay. So let me present. Okay. So this is the first question that we will be doing. So an LTI system has been given to you, the transfer function of a LTI system, and it is told to you that the input is cos of 3t and the steady state output is a sin 3t plus alpha. Then the value of a you have to find, and as added you also have to find alpha. So you find this a magnitude and you also find the phase contributed by it. So I will be giving you 3 minutes time, and then I would be asking you what results you get. So start solving that sum, and then we'll discuss.
B.
Okay. B. So what is the angle that you are getting? Your what is the
Minus
angle?
126 point, minus 126.86.
Minus 126. Okay.
0.86.
Okay. Anybody else other than Anubhav? It was Anubhav, right?
Yes, sir.
Okay. Anubhav, have you seen the question carefully? It is sine of 3t plus alpha. So you have 2 more minutes left. Anybody else with the answer?
B. Magnitude is B. I'm calculating it.
Okay. Try to find the angle and tell me.
Option B.
And what is the angle? What is the angle you are getting? Who was that who said option B? What is your name?
Abhishek.
Abhishek.
Yes.
Okay. Okay, Abhishek Sharma. Okay.
Angle is 143.
143. Okay.
Yeah.
Okay. So 143 you got. What did Anubhav said? Anubhav, what did you? Was you getting? What were you getting?
Minus 126.86.
Minus 126. Anybody else? Navkirti, what is the answer that you are getting?
Uh, Actually, I don't know the approach. I'm not getting it.
Oh, this is nothing you have to know. This is, class 12 trigonometry. It is nothing you need to know much.
36 degrees alpha.
Okay. Yeah. Yeah, right. Minus of 36 point something. Okay. Let us see how we are getting it. So the first thing that you have to keep in mind is when, input is given to you, cos of 3t is given to you. Okay. So this is an LTI system. It is not going to change your waveform at steady state. So whatever you give input, it would produce similar output. I mean, by similar I mean the waveform or the wave shape would be very much similar. Okay. So what difference would it have? The only difference that it would have is the magnitude and the phase. This system would either attenuate or amplify the signal that you have given at the input, and it will produce, it may or may not produce some phase to it. Okay, so if it is so, what we need to do is we just need to find out what amplitude this transfer function Hs has at omega equal to 3 radian per second, because we are giving cos of 3t. That means we are just inputting a sinusoidal signal of a certain frequency to this transfer function, and we want to see what amplification or attenuation this transfer function produces to this signal. Okay, so what I am going to do is I have replaced s with j omega as usual, and then I have tried to find out the magnitude of it. That would be 1 divided by omega and this root over of 16 plus omega square. And what is the angle contributed by it? That is minus of 90 degree minus tan inverse of omega divided by 4. So we are interested only at only when omega is equal to 3 radian per second. So let us replace omega with 3, and what we end up getting is mod of h of 3 is equal to 1 divided by 3 root over of 9. We have replaced omega with 3, so 9 plus 16. So that gives 1 by 15. Now let us look at the angle. Okay, so it is minus of 90 minus tan inverse of 3 by 4. Now, so what we have is cos of 3t minus 90 minus tan inverse of 3 by 4. Okay, now cos is an even function. I take minus as common. What I get is 90 plus tan inverse of 3 by 4 minus of 3t. Okay, now cos of 90 minus theta would be sine of this theta. So 3t minus tan inverse of 3 by 4, I am saying this is theta. So cos of 90 minus theta would be sine of 3t minus of theta. So minus of tan inverse of 3 by 4. So what I am going to get is 3t minus 36.87. So the angle is minus 36.87 and A is 1 by 15. So this is the first sum that we had. Okay, is it clear to everybody, or somebody has any confusion? Anubhav,
Yes.
is it okay? Why
Yes,
was the
sir.
mistake that you are committing? Why weren't you getting 36 point something?
Minus 126.86. I didn't say that. I think input is to sign input.
Okay, okay, that is a common mistake. So I mean, these things happen very often. So be careful while solving. Shahadat, you said 146, right? Why? What was the mistake that you are committing?
I told 143, so
Uh-huh.
While converting from cos to sin, it was cos of 90 minus theta, right? I did it as cos of minus of 90 minus theta. So I added an extra 90 degree.
Okay,
So I got
adding.
minus 36 and I did 180 minus 36. So I got 143.
Okay, 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 okay. Okay, that would be our first sum. Let us move on to the next sum. Okay, let us move on to the next sum. Let us see what the next sum was. Okay, okay, okay. Another very simple sum. So in this sum, impulse response has been given to you, that is ht equal to e to the power minus 5t ut, and the output of the system has been given to you, and you need to find the input which is producing this output. So you can quickly do and tell me what answer you are getting. So just by seeing which two options can you eliminate?
C and D can be eliminated.
Correct, absolutely correct.
B.
B, okay, yes.
B.
Okay, what is Shadat? You
Yes.
were that? Okay. So you both are saying it is B, right?
Yeah.
Okay. Let us see what others say. Abhishek, you are up with the answer or you are still waiting?
Solve converts.
Okay, okay. Anybody else with the answer? Nafkirti, have you done it? It is a very simple sum. Abhishek, have you solved it? Sonali, have you done it? Pooja Sri, Sonali, Naimisha, if you are not responding, it is useless, to conduct live session. These live sessions main intention is for interaction with the students. Anyways, let us go ahead. This is a very simple sum. I do not know why you people are taking so much time to solve this sum. So the first thing that we have to do is you have to convert this time domain into Laplace domain, because in Laplace domain the output becomes multiplication of the Laplace domain, Laplace transform of the input and the Laplace transform of the impulse response. Okay, so what I have done is ht is given to us, that is e to the power minus 5t ut, and I have taken a Laplace transform of this. Why have I done it? Because you see, to find the output yt, is a convolution of this impulse response and the input x of t. Now convolution is far more difficult to handle as compared to multiplication. So, and we know that convolution in time domain is multiplication in Laplace domain. So the simplest way is to transform that into Laplace domain. So I have transformed the impulse response in Laplace domain. That comes out to be 1 divided by s plus 5, and the output that has been given to us, that also I have transformed in Laplace domain. So once we do that, as I have told you that y is equal to hs into xs, we can easily find xs from here by y is divided by hs, and we end up getting 2 divided by s plus 3. Now we take inverse Laplace of this, we get 2 into e to the power minus 3t of ut. So the correct option will be B. It's a very easy sum. I do not know why people are taking so time for solving this. This may be a bit lengthy, so I will give you 5 minutes time to solve it. Okay. So open loop transfer function has been given to you. I mean, it has been told that the open loop poles of a third order unity feedback system are located at 0, -1 and -2. So the frequency at which the root locus is moving to the unstable region is k. Now 0 has been introduced at x is equal to -3, keeping all other poles to be intact. Now you have to choose among the following options which is true for the root locus of the modified system. So let me give you 5 minutes time to solve it, and then we will discuss.
Option D.
Option D.
Yes.
That was Shahadat, right?
Yes.
Okay.
Sir, B.
What did you say, Abhishek? Abhishek, no. Anubhav. What did you say, Anubhav?
B. Sir, I'm still solving. Let me
This
do
for
it
Bombay.
again.
This one you are talking about.
Yes. Yes.
Okay. Anybody else? Anybody else who has solved it? Abhishek, are you trying to solve it?
No.
Okay. So I'm worried actually. I do not know whether people are trying to solve it. There are only two people who are trying, Shahadat and Anubhav, and Abhishek is sometimes trying. But others are just they are not replying. Neither they are responding whether they have tried or not. Strange. Now, Kirti, have you tried the sum?
Yes, sir. I'm trying to this also.
Okay, tell me what your intuition is. Which options can you simply discard looking at the question itself? Can you discard any of these options out of these four?
Let me think, sir.
I'm giving
Sir,
three more
A
minutes.
option can be
Option
discarded.
C option can be discarded.
Sir, A.
A can be discarded. Okay. What else? Why are you saying A can be discarded? Now, Kirti, what makes you think that A can be discarded?
No, sir. K will act can be act as a breakaway point. So I don't think so.
B and C can be discarded.
Absolutely. Absolutely. That was Shahadat, right?
Yes.
Yes, you are correct. B and C can be easily discarded. See, the first thing is, so when you are adding a 0, it will have some effect. So the first thing is, it will not remain at K. So the point of intersection will not remain at K. So there has to be some change. Now, adding a 0 will have an effect of, pulling that root locus, branch to the left hand side of the S plane. So it would either be greater than K, I mean it can either be greater than K, or it can never touch the j omega axis at all. These are the two possibilities that you have. So you have to choose either between A or D. So B and C is never the option. B and C can never be an option. So you can easily discard these two just by looking at it. Okay, these two can never happen. Okay, having said that, let us go to a formal way of solving. So let us just first see how the root locus would look like when there are only these three poles. Okay, so let us do it. So if there are these three poles at s is equal to 0, s is equal to -1 and s is equal to -2, then the open loop transfer function would be some k1 divided by s plus 1 and s plus 2. This k1 is a variable gain, and I am trying to find the root locus, the locus of the closed loop poles as k1 varies from 0 to infinity. So for doing that, so first we need to find the characteristic equation. So 1 plus gs would give you the characteristic equation, and the characteristic equation is written as this. Okay. So now we are interested in finding the intersection of the root locus with j omega axis. Now how do we do that? So the only the simple way of doing it is with taking the help of route array. So we first construct a route array like this, as I have shown on this slide. So after constructing the route array, we see this element 6 plus k, 6 minus k1 divided by 3. So we find that this element, if this element goes to 0, that means that there has to be two poles on the imaginary axis, and the location of the poles should be given by the auxiliary equation, which is written as 3s square plus k1. So if you solve the auxiliary equation, it would give you the exact location of the poles on the j omega axis. That is what I have done in this slide. So I have told that when this becomes equal to 0, when this becomes equal to 0, when k1 equal to 6, when k1 equal to 6, this element would go to 0, and if this element goes to 0, I know that there are two poles which are existing on the imaginary axis, and how to find the poles? You have to solve the auxiliary equation for that. The 3 of s squared plus k1 equal to 0, where k1 is 6. So this is what I have done. 3 of s squared plus k1 equal to 0. Now to find the intersection, we replace s with j omega. So if I replace s with j omega, what I have is minus of 3 omega squared plus k1 equal to 0, and then correspondingly we find the frequency at which it is intersecting, and this √2 radians per second has been given to you as k. Now we note that k1 has to be greater than 0, right? Because or else this root over of this imaginary thing, root over of this negative thing will not exist. So this has to be, k1 has to be greater than 0. Okay, this is something that we have to keep in mind. Having said that, let us move and see how the root locus plot would look like. So we can find the angle of the asymptotes, that is given by odd multiple of 180 degree divided by total number of poles minus total number of zeros. There are 3 poles and no zeros, so 180 degree divided by 3, that is 60, and then multiply it with odd number 3 into 60, that will 180, and then 5 into 60, that is 270. So there are 3 asymptotes, one which is lying along this dotted line, the other which is lying along this real part of s, this axis, the x-axis that we call, and the other asymptote which will be along this line, that is which is subtending around 270 degree from this real of s axis. Okay, so the root locus would be starting from this open loop pole. It would be meeting somewhere over here, it will break away at this point, and then it would be asymptotic to these two lines, and the other branch that will be along starting from -2, and it will be along this real of s. This is how the root locus would look like. Now what you have done is you have added a 0 somewhere over here. What effect does a 0 have? It would pull this root locus towards the left hand side of the S-plane. So this will be pulled towards this, the left hand side of this plane. So if you pull this, the point I was making at the very first slide, this intersection will go up. So k may be higher, or it may not intersect at all, it will be asymptotic to this line. So you can easily eliminate the other two options. So the effect of adding 0 would be making the system much more stable, and it will be pulling this root locus towards the left hand side of this plane. So the intersection will not be over here, it may be over here, or it may not intersect at all. Now our dilemma is it intersecting, or is it not intersecting? Now one thing that you can readily see or readily find out is, after adding the pole, if you try to find out the angle of the asymptotes, it would be 90 degree, and the centroid would be 0 0. That means that your asymptote would be along this would be imaginary part of s, that is j omega axis. This would be your asymptote if I put a 0 over here, because you see 180 degree divided by 2, because there are 3 poles, 1 zeros. The 3 minus 1 is 2, 180 divided by 2 that will give you 90, and then odd multiple of it, that would give you this angle. Okay, so again what I am trying to do over here is trying to add this 0. So s plus 3 is a 0 that I have added over here, and then I am trying to write the characteristic equation. The characteristic equation becomes somewhat like this, and from here what we do is we construct the route table. And what we observe in the route table is, you see, we have told in the previous slide that k1 has to be greater than 0, and what we see from the route array is all the elements in the first column of the route array is positive when k1 is positive, and k1 is positive, that we have established in the previous slide. So if that is so, the root locus can never intersect the j omega axis. So how the root locus would look like? The root locus would look somewhat like this. So it it would be starting from this open loop poles, it would be meeting somewhere over here, and then it would be asymptotic to this imaginary j omega axis. And there is another branch of the root locus which starts from this pole and it ends at this 0. So this is how this is how you need to approach the sum. Now let us move over to another sum. This sum is a bit tedious, but it will teach you something. So one thing, what is the key lesson that you learned from the sum that I just showed? Anubhav, what is the key thing
Yes,
or the key takeaway point from the sum that you have just done?
uh, sir, I didn't consider zero. So the angle of asymptotes become 90 and it approaches infinity. I just solve by I just take the frequency, putting minus omega square plus k is equal to zero.
No, first try to build an intuition first, so that sometimes you may commit a mistake and you end up getting a result. But when you have an intuition for it, then you can say whether the result that I'm getting is correct or not. First try to build an intuition, just like what Shahada just pointed out. When there is a zero, it would pull the root locus on the right hand side of the S plane, left hand side of the S plane. So it would make the system far more stable. So there is no way by which the frequency can be less than k. So one thing that you have to keep in mind, that whenever we add 0 on the left hand side of the S plane, like the 0 that I have just added, it has an effect of pulling the root locus towards the left hand side. It makes the system much more stable. Okay, this is one key takeaway point. Another sum I will give you. This is a very old sum. This sum has appeared in 2002, but this has something that you can learn from it. So I have added this sum. You can just try this out. Okay, this is a good sum and it has some insight in it. So what is the new thing that you see over here is, see, how have we defined root locus? Sharat, how have we defined root locus? What is root locus? What locus are we drawing?
Locus of the closed loop
Poles, yes. Locus of closed loop poles when what is varying?
and K, the gain of the open loop gain.
The open loop gain of the system is varying from 0 to infinity.
Yes.
Now look at this sum. What is varying over here? Is the gain varying?
An open loop 0 is varying.
The open loop 0 is varying now. Okay. So one thing that you have to learn, that you keep in mind, is root locus. With the help of root locus, it is such a strong tool. With the help of root locus, you not only can study the effect of variation of gain, but you can also study the variation of any pole. If there is uncertainty in the pole, you can find out what how the closed loop poles would will vary, wander about in this plane when the when an open loop pole is varying from 0 to infinity, or open loop 0 is varying from 0 to infinity. So that is one important lesson that you can learn from this question. So what you have to do is you have to sketch the root locus, and my question would be how to go ahead with this. How are you planning to do this?
We can separate them as two transfer functions.
You can separate, but for root locus you need to write the characteristic equation first. How will you write the characteristic equation? Anubhav,
Yes,
how would
sir.
you approach this sum?
So by the rules,
By the rules, you have to first write the characteristic equation. How would you get the characteristic equation over here? Because gain over here is not varying. What will you vary from here?
angle, sorry, 0.
How would you modify, or what will you do so that you can use the rules that you know about the root locus? You have to do some mathematical manipulation. Anybody else who has an idea? Nafkirti?
Sir,
Yes
it's
sir, अब फर्स्ट वी फाइंड कैरेक्टरिस्टिक इक्वेशन, लेकिन उसके बाद अल्फा का वैल्यू वेरी करते करते एक्स का वैल्यू कैलकुलेट करेंगे सर, और फिर उसको कोऑर्डिनेट में देखते हुए वैसे बता सकते हैं सर।
How would you do it? I mean, you are not given a computer over there so that you do some numerical method to find your answer. You have to modify it in such a fashion so that the conventional root locus rules you can apply. Okay, so I would tell you how to do it.
Angle 180, angle pi,
Angle.
angle is equal to pi, angle condition.
No,
Angle
that
condition.
condition is when you have a open loop system and you know a point is lying on the root locus. But my question is, how would you write this characteristic equation so that this appears like a gain? So you have to do some
1 plus that g of s, and
1
after
plus,
solve.
yes, 1 plus g of s, then 1
Then,
plus g of s gives you characteristic equation. Now what will you do?
sir,
लॉग
round
भी लगाएंगे
with,
Yes, Navkirti, you are trying to say something. Tell me.
sir, round with criteria.
No, we are not going into the steps. I am just asking the first step. What will you do at first?
So first we should write the characteristic equation, and then it will basically be, and then we can shift the s term.
Okay, let me show you how to do it. Okay, see. So 1 plus this is the GS, the open loop transfer function. Okay. So now the characteristic equation becomes this, and then if you simplify it, it becomes ss cube plus 12 of ss squared plus 22s plus 2 alpha, it becomes equal to 0. Now you have to modify it. You take this as common. So if you take this as common, what we have is 1 plus 2 alpha divided by ss cube plus 12 ss squared plus 12s. Now do you see that this appears to be similar to what you are accustomed with? The open loop, the new modified open loop transfer function. Now alpha is appearing like a gain rather than appearing like a pole, like a 0, right?
Yes, sir.
Now we can say that this is not equal to 0, because we have seen in the characteristic equation that this is not equal to 0. This plus 2 alpha equal to 0. So this cannot be equal to 0 for any point on the root locus. So this portion has to be equal to 0. So if that is so this becomes our new characteristic equation, modified characteristic equation, or a new characteristic equation. Now we considered a open loop transfer function where gs equal to 2 into alpha, and I factorized it. So we have s into s plus 2.25 into s plus 9.74. So this becomes your modified transfer function. Now you can use the conventional rules of the root locus that we have. Now what do you know? The number of asymptotes is equal to number of open loop transfer function poles minus number of open loop transfer function zeros. 3 minus 0 becomes equal to 3. The angle of asymptotes can be found out by odd multiple of 180 degree divided by n. So this gives you 60, 180 and 270. And then you find the centroid of the asymptote, that is sum of the pole locations minus sum of 0 locations divided by n. That gives you almost equal to minus 4. To find the breakaway points, you write alpha in terms of s. You then differentiate alpha with respect to s and equate that to 0. If you do that, you would end up getting s equal to minus 1.056 and minus 6.94. This cannot lie on the root locus because to the left of this point we will have even number of poles. So the only breakaway point that we'll have is this. Now to find the intersection with j omega axis, we have to use route array. So we write the characteristic equation again, and we end up getting this table that I have already told you almost 1,000 times now how to form this table. And after that we find that to make to have intersection with j omega axis, this element has to be equal to 0. For that, alpha has to be 264 divided by 2, that is 132. Now the intersection with j omega axis would be the solutions of the auxiliary equation, which is given by 12 of s square plus 2 into alpha, where alpha is 132. So you put that and you get omega equal to root over of 132 divided by 6, that is 4.69. So this would be the intersection with the j omega axis and the root locus. So after that, I have drawn the root locus for you people. So let us zoom out. So you see the asymptotes are they are meeting at minus 4,0. There is a pole at minus 9.74 and there is another pole at minus 2.25 and another pole at 0, and then they are they are starting from the open loop poles. They are meeting at some point, then it breaks away to the imaginary to the complex plane, and it is becoming asymptotic to this asymptotes, and the intersection with j omega axis would be plus minus j 4.69. So this is how you solve the sum. This is an important sum that sometimes you need to keep this in mind.
सर
Yes.
जो क्वेश्चन था सर, सबसे पहले हम कैरेक्टरिस्टिक इक्वेशन करके अल्फा का वैल्यू वेरी करके रूट लोकस तो ऐसे भी तो ट्राई कर सकते थे सॉल्व करके। रॉन्ग प्रोसेस।
क्या what are you saying? Can you please repeat?
जो भी मेरा आंसर फंक्शन दिया हुआ है सर, तो सबसे पहले उसको हम कैरेक्टरिस्टिक इक्वेशन कैलकुलेट करेंगे सर, और उसके बाद
after that
उसके बाद अल्फा का वैल्यू चेंज करते करते फिर एस का वैल्यू कैलकुलेट करेंगे, मैं सॉल्व करेंगे इक्वेशन को।
the alpha is varying from 0 to infinity.
यस सर, and then
How would you plot this? How would you draw the root locus for alpha equals 0 to infinity?
सपोज करते हैं सबसे पहले अल्फा का वैल्यू 0 है सर, उसके बाद इस इक्वेशन को सॉल्व करेंगे सर।
Say alpha equal to 4. Say alpha equal to 4. Okay, you are getting a cubic equation. How would you solve a cubic equation?
जैसे हम सर यस सर विद कैलकुलेट मतलब लॉन्ग प्रोसेस है तो कॉपी बनाना।
That is not for human beings. What you are saying that cannot be done by human beings. That you have to write a code in MATLAB to plot the root locus.
यस
Okay, so that you are here to learn how to solve sum in gate examination, not to code in some in some software. So you have to know how to gate sums are like, I mean, you have to use your brain to find an easy way out to do the sum. They are not going to give you a tedious sum, a huge tedious sum. They generally avoid, because you have a short period of time and you have to answer it. So they are not going to give you sums which are very tedious. So whenever you are finding that sum is going too long, be a bit skeptical that I am doing some wrong somewhere, because it shouldn't be that lengthy.
यस मतलब मैं ये प्रोसेस बता रहा था दूसरे मतलब कॉपी बनाने मतलब ऐसे कैलकुलेटिंग इक्वेशन।
Okay, so that would be all for today. I have shown you 4 sums. Okay. Nothing more I have. I will have an exam coming up on 20th of October. 19th of October I would be a bit busy with my studies and all. So maybe I mean the next class, if I find time, I will be teaching you asymptotic Bode plot. If I don't, then maybe we will be doing that some later date. Okay, will that be okay? Will that be okay for everyone?
Yes, sir.
Okay, so let
Yes,
us
sir.
end today's meeting. It is already 7:55 in my watch. Okay, so let us stop the meeting today. thank you everyone. Enjoy your weekends and have happy Dashera to everyone.
Thank you,
Thank
sir.
you.
Thank you.